And yeah, I'm going to talk about a model-driven approach for the domain of machine learning monitoring. And yeah, I'm going to explain exactly what I mean by machine learning monitoring and how model-driven engineering can work in that domain. Since I don't know everyone, I see some familiar faces, but not everyone. So I'll just give a little bit of background. So yeah, as Stephen said before, I work for BT, and I'm also a PhD candidate for the University of York. Yeah, we work together as part of a European Union project. And in general, I'm in the Beta Lab team in BT, and we are looking at ways to increase, the productivity for people that write software for a living. So yeah, just automate certain aspect of their work to make their lives easier, make their code platform independent through, containerization, for example, running on the cloud, stuff like that. I try to use principles from model-driven engineering, but other researchers on the team have their own approaches. For example, some people try to use AI and machine learning to automatically extract data from large code bases and using that information do certain activities. Yeah, such as trying to migrate from legacy code bases to newer approaches and stuff like that. So yeah, as a general general information, this is what we try to do in this research theme. But today I'm going to talk about the problem of monitoring machine learning models in production and how I think that model-driven engineering can help solve that problem. So yeah, a little bit of motivation for people that don't work in that area of machine learning. So yeah, the idea is, the general idea is that a data scientist uses a large data set of examples to extract like a general rule, and then using that rule, they can make some predictions about previously unseen examples. The problem is that once you train the model from a static data set and you deploy to production, you have no guarantee, essentially, that the incoming data is going to have the same statistical properties as the training data. So it is considered a good practice to continuously monitor the newer incoming data and make sure that it is similar to your training data. So yeah, we want to detect any sort of changes in the environment and apply corrective measures, as I say here. And since this is a little bit abstract, I always present like a small example that I thought of. And I know that some people here have seen this before, so bear with me. But yeah, the example that I always use is that we are, in a company's call center. For example, BT has some call center, and people call all the time to say my line doesn't work or my internet is slow, etc. And yeah, we have like company representatives that pick up the phone, try to resolve the problem, etc. So in this example, we might be like a data scientist, and we try to predict whether a client, like the company's customer is going to be happy or not after they call our call center. So in this example, the two features, the two variables that we have in our possession in order to determine whether the customer is happy or not is the wait duration, the amount of time that they were put on hold before speaking to a human, and the service duration, the amount of time that the actual spoke to the company's representative before hanging up the phone. And I said, completely arbitrarily, that if the sum of the wait duration and the service duration is below 20 minutes, so like 1200 seconds, the customer is going to be happy, like a plus sign here, and if it's more, it's going to be unhappy. And yeah, we have this labeled data set, and we run a simple linear classifier, and we come up with this decision boundary, and we say, okay, for every customer in the future, we take their wait duration, service duration, and if the sum is below 20 minutes, we predict that they're going to be happy. And as we see here in our training data set, the wait duration has a mean value of 600 seconds, 10 minutes, and the service duration is similar as the wait duration, has a mean value of 10 minutes, and they have like a standard deviation of 3 minutes, and they follow like a normal distribution. So all of this information implicitly affects the model that we are going to come up with. So over time, one scenario that might appear is that of data drift, or some people say, covariate shift or prior probability shift, if they work in statistics, if they have like a statistics background. So yeah, it has multiple names, but in general, like data drift. So the incoming data changes, some of its properties changes. For example, here, instead of having a mean value of 10 minutes, the wait duration shifted and has 15 minutes. So that can somehow might affect the accuracy of our model. Yeah, if we come back to the call center example, so this might happen, for example, if one day we don't have enough representatives to pick up the phones quickly enough. So, the amount of time that the customer is put on hold increases. Another one might is called concept drift, and it means that even though the wait duration and the service duration hasn't changed, it's statistically the same mean value, same standard deviation. The mapping between input and output, so whether one is happy or not based on the wait duration and the service duration, has changed. So it used to be, if the sum is below 20 minutes, right? It has shifted, and it's if it's below 25 minutes. So over time, people's expectations change, right? So they become more accustomed to waiting a little bit longer. So of course, if we change nothing and we continue using this decision boundary, our predictions are going to be wrong, or at least not as accurate, I should say. So yeah, and of course you could have both of them together, and this is where things become even more difficult. So both the incoming data has shifted, and the mapping between input and output has shifted. And of course there are like various tricky situations like virtual concept drift or sampling bias. in which our initial training data set was not representative of the whole universe. So chunks of data from here and here are missing from our training data. So we thought that this module is good enough. I'm sorry, this one, yeah, solid one. But after we run in production, we see that actually this one is the real one. But strictly speaking, it's not a real concept drift. It's just because we didn't have a representative training set in the beginning. So yeah, some people say virtual concept drift to differentiate between the two. So yeah, just some of the scenarios that can appear. So okay, what can we do about that? You might say. Ideally, we would have a system that doesn't just serve predictions, right? But it also monitors the inputs and the outputs of the model over time. So yeah, we would and over time we would like to run an algorithm to say, okay, in the past few days, is everything as expected? And if not, do something, right? So we specify an algorithm to run every couple of days or weeks or months. We have a storage system. So whenever we receive a new data point, we just store it for future reference. We might even have a system to retrieve like ground truth labels. Not for every incoming sample, of course, but maybe we can do for a subset of them to see, okay, is everything going well? For example, send a text message to 10% of the customers and say, were you happy with the service that you received? And see if our prediction matches their feedback. So yeah, we have a system to execute the algorithm on a schedule, and of course we need some kind of way to react in the scenario that we do indeed detect some kind of drift. Okay, so with that in mind, how can we make a system? And now we come to the model-driven point of the presentation. So how can we make a system such that the data scientist can describe this kind of monitoring system without having to worry about the underlying technical implementation of the system? So for example, they can provide us with their machine learning model, of course, the algorithm that they want to apply, and a domain model, so a model in the MDE meaning that gives us all the information that we can use to generate the system that has the behavior that they specified. So they can tell us and how often they would like to run the algorithm, what to do when drift is detected, so on. And then with this information at hand, the platform will automatically deploy the machine learning model to a web endpoint, provision database to store all the incoming data, ingest the incoming data, so we put them in a database, ingest the feedback, the ground truth, run the algorithm on a schedule, and for example, send email alerts to the data scientist to notify them that something is not going according to their specification. Okay, so how would the workflow look like from the perspective of the data scientist. So, as I said, they write their ML model, they write a small MDE model, and I will show the details of that. They send it to a code generator, and the code generator can output, in this example, Kubernetes manifests that can be used to deploy this whole system to a computing cluster, to a Kubernetes cluster. So yeah, this is just one concrete implementation, and we target Kubernetes, but theoretically, by changing this part over here, you can target anything you want, and the data scientist wouldn't even know it. So this is the idea, to decouple the description that the data scientist provides from the actual thing that runs on our infrastructure. So as a first approach to this, we developed this meta model, right? So we have an overall deployment of the whole system that serves predictions and also does all of the other stuff. And the deployment has a model with some information that we need about that model, and this model expects certain inputs and gives certain outputs. And the system also has information about drift detection executions. So, and this more specifically can be a data drift detection or concept drift detection, and with all the accompanying information, such as the frequency in which this will be executed, what will happen, so on. And so, according to this meta model, the data scientist can construct their own model. For example, this is in FlexMI format that can be understood by the Eclipse modeling framework we've used to write to construct the MDE part of the system. And it's very simple YAML that the data scientist already is familiar with, and it has all the fields that are required by the meta model. Okay, so if this is fed to the generator, we get this thing back. Generally speaking, we will get, of course, a Kubernetes manifest, so a text file, but this is what it describes. So you have a system which includes the machine learning server that serves the requests, of course, and you have various other things that are required for the rest of the functionality. For example, you send every request received, you send it to a database writer that writes the inputs to a database for later usage. You have a system that you can ingest a component that ingests feedback to the database, and periodically you run a drift detection algorithm that gets data from the database and, for example, historical data, your training set from cloud storage, and runs the algorithm specified by the data scientist and sends, for example, email notifications. Yep, I'm wrapping up. Yep, almost done. So, and the last part is that in order to alleviate the need for the data scientist to write things by hand and run the generator in their local machine, and then deploy the Kubernetes manifest to the cluster. So in order to automate all of that, we also made like a small web app that streamlines all of this process. So they can write their model here and some auxiliary functionality here, such as uploading their machine learning model to the cloud, stuff like that. So yeah, this is also deployed in the same cluster, and but yeah, anyway, it's not that interesting. And so some future work to make this more robust, more complete, would be to provide a way to incrementally update this whole system. For example, if the data scientist wants to just change one thing, for example, the frequency, or add some drift detection algorithms, but they want to keep everything else the same, they can do this incrementally. Provide more ways to schedule things, not just based on time, maybe based on the rate of incoming data and stuff like that. And of course, provide more reactions to drift, not just email notifications, maybe automatically trigger a retraining pipeline and stuff like that. So yeah, that's pretty much it.